All right, we'll get started. Okay. So let me quickly recap, okay, where we were last time. Okay, so once again, the flow of the course is that before we talk about anything about prom, we want to make sure everyone understand a little bit how the large language model has been built. Okay, although it's a very complicated process, we're trying to give you the really most fundamental um, simplest tutorial example, you can see the steps, okay, but nothing close to the actual technology they use. But the steps, I think the same thing. Okay, so we start to introduce machine learning. We talk about the two major type of machine learning. One is regression, one is the classification. And then last time we were talking about how do we use classification to build a very simple language model. Because when we talk about predict the next word based on a given input and sentence. That process is a classification. We're trying to pick one word from a list of words. So it's a pick one category, right? So this is what we did last time. We gave some sample sentences inputs, and then we formed the table. We just look at the very last word, right? So that word go to the last column as a target column, and then the first whole sentence is the input column. And then the main thing we are trying to solve last time was how do we encode all the strings, because the machine learning models only handles the numbers, and then you want a very clean, organized numbers, not like a random different lengths, right? So that's why we introduced this vectorizer. And then the easiest one is something called a count vectorizer, right? So we build a little vocabulary, a dictionary of all the words, and we give them index, and then we just count how many times each word shows up. And then based on that frequency, we build a little like a matrix like this. Okay. And then once we have this very nicely clean the 2D kind of a array or list of lists that fits into our sklearn library very well, right? So we can start to learn and then train it. Okay, so we were showing how do we use SVM, the most popular classification algorithm to do the training, and we try some of the results actually works very well, right? And then I also mentioned there are a lot of other complicated vectorizers to handle the text. The TF-ID is some kind of reverse frequency. They pick the word that you don't see very often. Normally, we think these words are more special, right? We talk about other things, and then we also mentioned the BERT, which is the transformer um, model that is basically technology used today in the large language model. Okay, so anyway, so there are different vectorizers and you can change them. We also mentioned about uh, how do we bring some randomness, okay? Because as we use ChatGPT, not every time we got the same results. So how can we make sure we see some differences? So we use the probability based on the machine learning model's results. If the probability is higher, we'll give more chances to certain words. Otherwise, we'll give you less chances. Okay, so that's where we're. So far, this is already a very good example on how the large model works. Okay, given data set, pick model, training, prediction. Okay, so it's pretty good. Now, as you see this example, obviously, it's a very naive example because first of all, I think the data set is just so small. Okay, and it's 5 sentences. It's just really a toy. Okay. However, the data set isn't the most difficult part. We can always get more data, more sentence, more text. I mean, you do some web scraping, there's some data set. This one is not too hard to deal with if you just want to increase this data amount. But then the other part we're using is obviously the algorithm itself, right? So right now we're using this SVM model. SVM is a very popular model. Okay. In the past, most time when we're dealing with a machine learning problem, and then someone told me that you should always start with SVM, okay, because normally SVM provides a pretty good results. So start with SVM and see how it works. And if not, then you can try to change and compare different algorithms. Okay. We did some of the project before. Every time we run different experiments, SVM is often among the top performers. Okay. So there might be some cases, some other models, you tune the features, the parameters a little bit slightly, you got a slightly better result, but SVM is not going to be too much difference. Okay. So this is definitely some kind of very easy choices for you for the traditional machine learning problems. But for the large language model like this is not obviously not going to work very well. We need something more advanced. That's why today I want to give you a very quick overview on the deep learning. Okay, so as we talk about sklearn, scikit-learn, this kind of machine learning. Okay, so we normally define this as traditional machine learning model. A lot of those are based on mathematical models, where the deep learning model is different. Okay, so you might heard about the term called neural networks. So they use a totally different way of defining the model and not necessarily quite related with the math. It's about forming or simulating how the neural networks works. We all know like that's how the brain works, right? So we basically take the same idea and try to use a computer to simulate it. Okay, so that's what the deep learning is about. Okay, some of the quick introduction here. The basic example about deep learning model is that self-driving. Okay, so I'll just play this video here. Some of you probably seen this one. There are different versions. This actually came very early. Okay, so that's early days when Tesla was trying to demonstrate how the self-driving works. Okay, so you probably much want to see the right-hand side, all these cameras, three different cameras. They're recognizing all the objects in real time, right? So they can see their car, they can see the lane, as you can see. Obviously, they can also find out the sun, the building, and people walking, in trees, all the different stuff. The really cool thing is that they do this in real time. They also track multiple objects, and then they did it pretty accurately, so they can draw the bounding box, right? And if it's a car, they will know the direction, and once they can do the real time, they can know the speed. Now, if it's a traffic light or traffic sign, and this one, yeah, they can already see a little bit about traffic light. If you ever use the Tesla self-driving today, it's much more advanced than this version. Yeah, they definitely track the lane so well, the traffic light, the color, and everything pretty accurately. Okay. Probably 5 years ago, that self-driving when they just released, the local road wasn't very good. This year, if you ever try those, it's much better. It's definitely a lot better than before. It's still not perfect, but it's a lot better. But most technology behind it. Okay, so yeah, yes.
Just want to ask, so I remember you said you had a self-driving vehicle. Is it a Tesla as well that you had?
Yes.
Yeah.
So yeah, I was but you put the self-driving, but then you can still, cancel it by pushing the steering. That's what happens. That's what happened. I wish that they can keep the steering wheel. Anyway, it's pretty reliable. If you ever use that one, it's much safer. It's much safer than you drive manually.
Especially in LA traffic too.
Exactly. Exactly. Yeah. But anyway, so the cool thing about Tesla self-driving, the reason people think they are the leading player in this field is because they do most of things with the cameras, right? So they don't use the laser scanner. Sometimes you see the car like a Vimo. If you've been to San Francisco, they have the taxi, right? They put like a five, six different sensor radar or laser, whatever they call it, all around the car. They use the hardware to scan the nearby building stuff. Yeah, so very good, obviously very accurate, but there's a cost, there's all this extra stuff. But Tesla pretty much did most of the things just with the camera. They have multiple cameras around it. Um, so they were actually in the early days, people don't trust that this is going to work because you can show a demo like this, but there's always going to be some accuracy. People think, for self-driving, you can't rely on those. But it turned out that it works really well. So that was a very, very big deal just using cameras. Okay, but anyway, so we're talking about today, like all this bounding box you see, you capture the object, recognize those. That process is also machine learning, right? So you have some kind of images here, some pixel here. How do you classify it? Do you classify as a car, as a tree, as a person? It's a machine learning problem. It's a classification problem. Okay, but the algorithm they used is not SVM. Okay, they use neural network to do this one. Okay, so you see a lot of this kind of examples before that different cases, but the fundamental thing we're trying to do here is given a little image, okay, you tell me what object that is. This is the more advanced version. I give you a big image, and then you tell me all the different objects you could recognize inside it, and also give me a bounding box. Okay, so that's what the technology can do. All right. But going back to the very simple and classical example, okay, in early days, researchers were mostly trying to figure out how do we let computer to differentiate dogs and cats. And for us, it's a very simple task, but for computer, it was only like 60 to 70% of accuracy. I would say maybe 10 years ago, 10, 12 years ago, we can only get to about 60 to 70% of accuracy, or maybe 10 to 15 years ago. Okay. This has been a very, very challenging task for us because think about this one. This is a very difficult. Now think about an image, right? You get an image. It's all like pixels, like a 2D array, every number representing some kind of numbers. Sorry, the color, right? That's how they represent the image. So now we ask you to write a program to take that input, the 2D array, tell me whether it's dog or cat. Just from a programming point of view, it's a very difficult task, right? How would you do that? Different size, different type, different color, different background, the face different, not to mention there are different type of cats and dogs. How could you ever write some rules, for example? Okay, if you see the eyes is this size, the ratio is this size, then this is a cat. It's very difficult. There are too many variances, right? So that's why it's a very difficult programming task to do. So people only get to 60, 70% of accuracy. Okay. But now nobody talk about this problem because this problem has been solved completely. Right now, I think the accuracy is already above 98%, 99%. Obviously, there are some kind of very added cases that maybe human cannot really tell if this is a cat or a dog. It's a very special type, but overall, this is very good. Okay. Now the solution what to this is all this using neural networks to train the models to let computer to learn it. So the idea here is the same thing. They go the same process of a training process. Okay, so they find a lot of data set that they can see here. There's so many different cats, so many different dogs, and then we need to label them. Okay, remember I told you what is called supervised learning. So you have to label them. You tell the computer these are cats, these are dogs, and then you provide the data, and then you choose a model and then they will try to figure out all of this by itself. So you don't have to worry about all the rules, the ratio, all of these things, because there are a lot of things you cannot really imagine. So you just need to provide a sample data set. And obviously, the more the better. It doesn't matter about the background. It doesn't matter about the shape, the size, the type of the animal. Just give them, label them, and then the computer will pick it up. Okay. And then eventually, they're going to form some kind of model. And as you train this, and obviously the input is the image, but then you have to, figure out a representation with the 2D array. And then you got some different kind of features, a lot of compute process. We'll talk about the process shortly. And then eventually, you actually come up with a decision. Okay, it's one of the types. It's a very classical or classification problem. Okay, this is how the deep learning model works. Okay, so they actually go through different, they call it different layers, and every layer they generate different amount of information, and based on that information, send it to the next layer, and then at the input, and then you generate another output until you finally get only you pick from the two choices. Okay, so this whole process you're seeing here is called neural networks. Okay, think about that. That's how the brain works. Okay, I'm not a biology person, but everyone probably learned some basic biology that in our brain has neurons, and obviously they're connected somehow, and then they transmit all the information. Again, I can't explain, but this structure, especially if you look at this animation, pretty much that simulate the same process. Now, this is very interesting. In fact, in computer science, or actually in other fields, a lot of the time humans are trying to simulate certain things based on how the real world works, right? So think about when people are building airplanes, they're trying to simulate how the bird works. That's why you have wings. In this case, the same thing, because we know that's how the brain works. So you build approach like this, it turned out it works really, really well. But previously we talked about the math, okay, formulas, that's not enough. And then when you get to this level, it's actually functioning just like human beings. Okay, so it's pretty interesting. A lot of times we're just copying the nature of the real world, how that works, and then put that into the different field. Okay, so this is also another good example. Another very interesting example, I don't know how many of you have heard about something called genetics algorithm. Anyone heard about it? A little bit, right? It's also very related with something called reinforcement learning. Okay, so you can Google a little about the genetics algorithm. It's a very interesting algorithm. So you might see some of the in YouTube, you can find examples that um, like they write an AI program to learn how to play games all by itself, right? You can see in the beginning it's just very stupid, and then later on it get really, really good. Okay, so that whole process normally called reinforcement learning, but the one key idea behind it is that they use um, this kind of genetic algorithm idea that how do you teach that? It sounds like a very complicated process, but the computer process very easy. So in the beginning, the computer just randomly choose a solution, totally random. The computer knows nothing about games, knows nothing about how to play. They just randomly choose how to play, and then you will see some of the solution will work slightly better, some of those work worse, right? So maybe the car goes further, or maybe you just die a little bit later. So you know which solution are better. And then what we will do next is we'll tell the computer, okay, this half was better, and where this half kind of sucks. I want you to drop the bad ones, keep the good ones. Now I want you to, based on the good ones, can you generate new solutions based on the good ones? So that's how the evolution works, the biology in the real world. And then if you keep doing this, you will see that the results getting better and better after each time you tell the computer which one is better. So you always pick the best ones and generate even better ones. And eventually you can see that's how the computer plays. Okay. So that example I also want to show you the algorithm is called genetics algorithm, right? So that's how all the gene like evolution, all these things works. Every generation were not exactly the same, right? There are variances, but we tend to go better and better because if the gene doesn't, it's not good, normally it cannot survive. So same idea here. Okay, so just some kind of a comment here that simulating the real world is normally a good direction. Okay. Um, Speaking of like all the whole image recognition classification, okay, I'd like to normally show a quick demo here. This is kind of a good example on how it works. It's actually today doing this one is really simple. I don't know how many of you use this one. You don't even write a code. The Google provide this platform. This came in a long time ago. Okay, so it's really easy to do. So if you want to train a model, okay, I told you you have to provide different samples. So here, let me try to show some demos here. Okay, I'm gonna pick some different object here. Okay, what I will do is I will just open my camera. All right, so the first top object is a paper towel. Okay, all right, so I need to provide some samples, and then you can use this one to take some different pictures. Okay, it's a paper towel. Okay, I'll do roughly 30 images. Okay, I'll give a label. All right, and then I'll do another one. Mm, listen here. Okay. So we'll do the second type where we have this. It doesn't matter like angle, like size. Okay, just give some kind of variance. Okay, I don't know. This is speaker, I think. All right, so we'll get another one. Um, Maybe I'll just use my phone. Okay, so just use the phone here. Okay, all right. So and then I'm gonna train it. So three object, okay? So these are the input data. Okay, same thing. And then as I type the label, these are the output data. Okay, so it's a supervised process. And then once I click on the train, then they're gonna take all the images and then they're gonna pick a model and then do the training. Obviously, this takes a little bit longer, but still really fast. Okay, now as you can see, it's already done. And now you can test it. Right now, we don't have anything. So they're just randomly predicting which one, right? So that bar shows the confidence. So it doesn't show you anything. So now I bring back the paper towel. Okay, as you can see, that actually go to the highest confidence. Okay, and then I bring back my phone, and that phone uh is good. Okay, and then finally, that thing is for sure it's a lot easier to recognize because it's bigger, the color, as you can imagine, it's a much more distinct, right? So that's a lot easier to recognize. Yeah, so that whole process it works really well. Okay, now this one actually, I think it's even training the front end with JavaScript. It's pretty fast and the results is really good. Okay, that's why today when you look at the image classification, it's no longer a big challenge. But then the algorithm behind it is all based on this neural networks. Okay. Um, all right. But the example looks very simple. Okay, I'm gonna close this one. But think about how this is gonna work, right? So if you remember um the process we normally talk, okay, so any kind of problem, machine learning problem, you define a problem first. And I like to draw a table. Like in this case, okay, our output column should be the type of object, whether it's a paper, it's a phone, it's a cup, it's a book, right? So that part is easy. What's really challenging is how do you define the input features, right? Since this is an image, right? So we're mostly talking about the visual features, you know, maybe like this one, obviously we want to look at the color. So color obviously differentiate the three things, white, green, and black, right? So the color matters. But a lot of the time the image has all different kind of colors. Maybe you want to look at the dominant color, or maybe you look at the percentage color, certain color in the image, right? So that's one type of feature you can come up with. Okay. You can all obviously, talk about other things, the total number of colors you see, maybe maybe the somehow certain kind of shapes or anything. So as you can see, this case, when we process the images, that input feature is pretty hard to define. Okay, it's not like the other example we told you before about the traffic, about the the flower type, just based on the measurements, that should be enough. And this one is way more complicated. All right. So that's why if you think about it this way, it's pretty hard um, to kind of define it, right? So that's why we need to use a totally different model. Like that's how the neural network came in. Just think about the brain, think about as we see a cat, okay? You never need to look at the cat and see, oh, they have white color, the eyes is this big. You don't really use that formulas. You just know it. The reason you know it because you've seen the cat enough. Okay, you see so many hats for so many years, and you know that is. But in your brain, it just obviously they capture certain important features. But now I ask you what the features are, you don't really know it. It's very hard for you to summarize it. Okay, that's exactly what's going on here with the neural networks. So you don't have to precisely define like what that feature is, but then you just gave some kind of a high level structure. Okay, I think this problem is complicated, so please generate different multiple layers and try to figure out the correlations between each one of them. So there is a YouTube demo here that animate the whole neural network process. I rarely play videos during the class, okay, but this one is really good. And also the neural networks honestly is a little bit abstract to understand. So I probably want to play this one for 3 5 minutes. It's a long video, but they have a series of videos that talk about all this machine learning deep learning problems. So this one is very worth to check out. Okay, so let me also provide a link in the chat. Okay, I don't know if you guys can hear the sound if you are joining in Zoom, but I will send this one here. All right, Carlos had a yeah, I had a question earlier. Yes. So yeah, to answer your question, yes, I was using that self-driving model, but that was not a machine's problem. Okay, that was my fault. It was not was a machine's problem because I actually touch the steering wheel. Okay. Anyway, if you're in Zoom, okay, take a look at that video. Spend like first 3 5 minutes. Okay, it's a very cool demonstration on how this one works.
This is a 3. It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea. while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future. But what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing, not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network, quote unquote, learning. This video is just going to be devoted to the structure component of that, and the following one is going to tackle learning. What we're going to do is put together a neural network that can learn to recognize handwritten digits. This is a somewhat classic example for introducing the topic, and I'm happy to stick with the status quo here, because at the end of the two videos, I want to point you to a couple good resources where you can learn more, and where you can download the code that does this and play with it on your own computer. There are many, many variants of neural networks, and in recent years, there's been sort of a boom in research towards these variants. But in these two introductory videos, you and I are just going to look at the simplest plain vanilla form with no added frills. This is kind of a necessary prerequisite for understanding any of the more powerful modern variants, and trust me, it still has plenty of complexity for us to wrap our minds around. But even in this simplest form, it can learn to recognize handwritten digits, which is a pretty cool thing for a computer to be able to do. And at the same time, you'll see how it does fall short of a couple hopes that we might have for it. As the name suggests, neural networks are inspired by the brain. But let's break that down. What are the neurons, and in what sense are they linked together? Right now, when I say neuron, all I want you to think about is a thing that holds a number, specifically a number between 0 and 1. It's really not more than that. For example, the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network. Now jumping over to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again, some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose two hidden layers, each one with 16 neurons, and admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment. And 16, well, that was just a nice number to fit on the screen. In practice, there is a lot of room for experiment with a specific structure here. The way the network operates, activations in one layer determine the activations of the next layer. And of course, the heart of the network, as an information processing mechanism, comes down to exactly how those activations from one layer bring about activations in the next layer. It's meant to be loosely analogous to how in biological networks of neurons, some groups of neurons firing cause certain others to fire. Now, the network I'm showing here has already been trained to recognize digits, and let me show you what I mean by that. It means if you feed in an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents. And before jumping into the math for how one layer influences the next, or how training works, let's just talk about why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What is the best hope for what those middle layers might be doing? Well, when you or I recognize digits, we piece together various components. A 9 has a loop up top and a line on the right. An 8 also has a loop up top, but it's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now, in a perfect world, we might hope that each neuron in the second to last layer corresponds with one of these subcomponents. That anytime you feed in an image with, say, a loop up top, like a 9 or an 8, there's some specific neuron whose activation is going to be close to 1. And I don't mean this specific loop of pixels. The hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits. Of course, that just kicks the problem down the road, because how would you recognize these subcomponents or even learn what the right subcomponents should be? And I still haven't even talked about how one layer influences the next, but run with me on this one for a moment. Recognizing a loop can also break down into subproblems. One reasonable way to do this would be to first recognize the various little edges that make it up. Similarly, a long line, like the kind you might see in the digits 1 or 4 or 7, well, that's really just a long edge, or maybe you think of it as a certain pattern of several smaller edges. So maybe our hope is that each neuron in the second layer of the network corresponds with the various relevant little edges. Maybe when an image like this one comes in, it lights up all of the neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with the upper loop and a long vertical line, and those light up the neuron associated with a 9. Whether or not this is what our final network actually does is another question, one that I'll come back to once we see how to train the network. But this is a hope that we might have, a sort of goal with the layered structure like this. Moreover, you can imagine how being able to detect edges and patterns like this would be really useful for other image recognition tasks. And even beyond image recognition, there are all sorts of intelligent things you might want to do that break down into layers of abstraction. Parsing speech, for example, involves taking raw audio and picking out distinct sounds, which combine to make certain syllables, which combine to form words, which combine to make up phrases and more abstract thoughts, etc. But getting back to how any of this actually works, picture yourself right now designing how exactly the activations in one layer might determine the activations in the next. The goal is to have some mechanism that could conceivably combine pixels into edges, or edges into patterns, or patterns into digits. And to zoom in on one very specific example, let's say the hope is for one particular neuron in the second layer to pick up on whether or not the image has an edge in this region here.
All right, so I'm gonna stop pause here. Okay, it's a very nice video demonstration, because the whole process was actually very abstract. But if you see this one, you think about it's really just a mapping process, right? So all the pixels form a list of numbers, and that number trigger an input and then produce an output, and then that output go to the next one. At the end, it does actually bring the idea of like breaking the numbers into little small lines and edges, and then based on the edges, it goes to shapes, and then based on the shapes, and then you recognize it. Okay, so but as you can see, this whole process is quite different from the regression or SVM classification we talked about before, where we can define a pretty precise mathematical model. And this one is not that. You never know what's inside actual works. Okay, so but you do know there are different layers, the number of layers, the type of layers. That's something you could actually define. Okay, so that is what a neural network is. It's a lot more complicated, but in this course, we're not going to dive into this too much. Okay, so have some kind of basic idea. But then, everyone need to know the differences here. Let me actually make this bigger. Okay, the traditional machine learning. So this term a little bit kind of confusing. Deep learning is a machine learning. Okay, but it's normally when we put this together, you should know. When you just talk about the machine learning, I would like to call it a traditional machine learning, and you just think about scikit-learn, the library we showed you in the past weeks. Okay, regression, classification, there's also another thing called clustering. And then deep learning is a type of machine learning, but this is obviously a very special type of machine learning that they just use neural networks. Okay, as you can see, these two examples showed you the differences. This is what we did for the past 2 weeks. Okay, we often try to figure out this is output, this is relevant input, right? So some of the features we precisely define and show it. Where the deep learning is more kind of abstract. Okay, we kind of know how many processes you need, and then you form a network here, and then you figure out the activation functions. How do you go from one input to another one? Okay, so it's a very different mindset. Okay, to summarize, neural network uses features it's learned on its own instead of using those handpicked by humans with machine learning. Yeah, that's pretty much how the two models works differently. Okay, so obviously that's how our brain works. Once again, when you're thinking, I look at the numbers. Okay, we can recognize all the handwritten numbers, no problem. But if we really ask you to define how do you recognize the seven, how do you recognize the nine, we really can't define it. Okay, so that's exactly what's going on here. Okay. So I want to dive into actually this example a little bit better because as you start to learn the deep learning and neural networks, you often will hear some of these terms. And the most typical one is called this convolutional neural networks, or they call it CNN. You probably see this term a lot. So the CNN is a very special type of deep learning model, or you can consider that as a kind of one way or one type of algorithm. Okay, just like SVM is one way to do the classification, and the CNN is one way to do neural networks. This one is so popular because this one actually does handle the image recognition or the object recognition problem we're talking about today. So the definition here is that this is a spatial type of deep learning model that's are pretty good at analyzing the images and audios, videos, this type of stuff. Okay, so they basically they take advantage of a spatial structure because all the images are represented by the 2D array with the pixels. So the structure here is very fit to handle that kind of problems. So what they're really trying to do here is just like the video mentioned, they're trying to find the edges. Based on the edges, they form the shapes and the textures, and then they can, make some decisions. Okay, so here I will just show you a very brief example how it works. Okay, the tutorial here is generated from ChatGPT. You can do the same thing, but I thought this is a very good demonstration. If you think about that handwriting example, okay, a number seven, if it's a very small image like this is a 4 by 6 2D array, just with zero and ones, and then ones represent the white and zero represent the black. So obviously this is the number seven. Okay, so as you can see, how do they define or detect the lines? Are that they apply a lot of these small filters. Okay, so they want to detect because for the handwriting, the lines matters. So want to see all the different type of lines. Where are they? How many are there? So first of all, they want to detect are there any kind of vertical lines. So this is a little filter they created. Now obviously we're trying to find if there is like all ones in the middle. So they apply this filter on this image. But then what they do is that they go through the subsets of it. You can't just directly filter it, right? So you just go to the smaller areas one by one and then detect all the little lines and where are they. Okay. So here's a more specific process. So let's see that the top part of the image, the first 3 by 3 image is like this. You apply this little filter and then you basically times one. You add them together, the result is one because there's only one spot right here that can match your filter, right? So that's why this part just gave you a one. In other words, that for the first 3 by 3 box here, there's not a very clear vertical line, but there's still something there. It's just a very short part, okay, at the top. So the value is one. But then if you go to this area, you apply this filter again, you will get a result of a two because there's one here can match it, and also there's one in the bottom middle here can also match it. So the result of two. That means this little box actually match this vertical line a lot better. So there's two. So you give a two value. Okay. So if you run this kind of filters all over the images one by one to iterate all the possibilities, and eventually you can get something like this. Again, the wider the color is, that means the better match, right? So if you think about, that's why the corner here has the highest value because the corner here is this area That's the example we talk about right here. So you got a 2 value. So that's why this one is a little bit wider. So applying the filters across the whole image, it generates the next output. Okay, so this whole process, applying the filter, you can consider that as the first layer, what they're trying to do. Detects all the different lines and then get this kind of matrix. And once you have a lines, then the next filter you can define what about the shapes, right? There's circle, they're kind of rectangle or triangle, things like this. And then eventually until you feel you can make a decision, right? So back to the dog and cat example, you can imagine that in the beginning you got some kind of pixel 2D array as an input, and then again the first layer will detect the edges. Based on the edges, we detect the shapes. Okay, the ears, the eyes, and then based on that, we kind of try to detect if the type is a cat or dog. Okay, so once again, the different layers they're trying to handle different aspects. But not every layer you need to define those accurately. Okay, so that's the power of the neural networks. All right. So for CNN, I hear there the because this is so famous, so everyone should know this more or less. Whenever you see the image classification example, most time people using the CNN to solve it. So Google provide a very good like a playground for you to try it. This one, I'm not going to type the code because the code for the deep learning a little bit longer. So let me just open it. You can open this sample code in the Google Colab. So let's just go through this very quick. So they start with importing the library. Okay, they use the TensorFlow. TensorFlow is the open source library. I think it's created by Google. That's the foundation for all the like a deep learning and neural network stuff. Most of the other libraries are built on top of this one. Okay. And then here they're trying to load the data. So they use a very famous classic like a data set. This is CFAR, this one. They have I think 10 types of images. Each type they have 6,000 images, they have a lot of images. And then you use that one as a training data set and you can do the testing. Now right here you can see what the image looks like. Okay, very small size images. Okay, very classical data set. So they get all the different animals, cars. There are 10 types, truck, frog. A lot of researchers use this one to run their algorithm to do the comparison. Okay. And then here is where you define your model. As you can see, you create a model and you use something called a sequential. Sequential means that the layers are one after another. And then you add a total of 5 layers, okay, convolutional, 2D, and max pool, all of this. The details I can't explain. Okay, you can find the purpose, but there is a purpose of each one of them. But they choose to form these 5 layers. And then here you can see that's how we set up, configure the model. Okay, so 5 layers, the combinational layers inside. And then we add some more dense layers just to make it, work better. Okay, so again, we don't explain the series because it's very hard to explain why they do this. Because after all the tests, it turned out this one to be really good. That's the final setup of the whole layers, multiple ones. And this process, if you see the model.fit, that's where we trigger the training process, the same process that we did before. Okay. Just right now, the model is more complicated. You write a little bit more line of code to set up the models by putting all the layers together. So you compile the model, you run the fit. This is where it takes most of the time because the data set is pretty large, 6,000 images, a lot of 2D arrays. So they run this one for different rounds. And every iteration, you can see the accuracy. They have some kind of accuracy estimation. So initially it's 30% to 50% right now. I think it's getting better and better. Okay, so this process take a little bit longer. Just the image is longer. The one I showed you from the teacher machine, that one took like only like half a minute to train it because I use only like 100 images. Okay, so they run this with multiple iterations, and then you can see the results getting better and better. All right, so eventually, as you can see, the accuracy is about 78%. Okay. They have some evaluation on this one. What they do is they use the image, some of the image from data set to test it, and then they can find out the accuracy, and the final accuracy is like 70%. Okay, so it's just a very quick, simple demo on how they. The most important thing you want to see here is all this setup. Okay, so the whole code is the same thing that we did for the traditional machine learning. The only difference is that the model here, as you can see, the setup is more complicated. Okay, you form a sequential model and you add all the different layers. Every layer you have a parameters. So the difficult part of the machine learning, or when you do the research, most of the time you're trying to figure out what kind of layer to use, what the parameter to use, and you run this data experiment to see which one was better, and you show the results. Okay, so that's where you need to put a lot of efforts. Okay, but the code is the structure is almost the same as the one we did before. And obviously, if you throw an image in it, and then they can also print out the label, the type of the image. Okay. So this whole process actually uses CNN or convolutional neural networks because you can see they put all the convolutional network here. All right, but then the approach is called deep learning or just neural networks in general. All right. If you know CNN, there's often another one called RNN, recurrent neural networks. Okay, so the CNN handles more normally a spatial structure. Like when we talk about spatial, it's like a 2D array. That's the best example for spatial. This one is more handling the sequence, okay? Especially the sequence between the previous one and the current one, okay? Just look at the examples, okay? So they show the example here. How do you use RNN to predict the next character, which is very similar to the language model. And next time we can take a look at how do we build a language model with RNN or other neural networks models. So you got hello, and then we're trying to predict the next word, which is a space. If you give this one, the next word should be a space, right? So what they do is that they first of all do some encoding, get a letter, give you a number. Okay, we're trying to predict what that next number is. Okay, so they do the training process. This part actually is very similar to it's very similar to the rock paper scissors example. If you remember, we look at the previous shows and then the current ones, and we form a data set. So right here you can see the first character is H, right? The previous one is 0, okay, because empty. So you got a hidden element here, it's called 0 and 1. And then you look at what's next. And next character is E, right? So that actually, the 0, 1, and E, that forms one set of the input. Okay, if you keep doing this one, and then the next word is E, and the previous one is H. Okay, so you combine these two, and then you look at what's the next one, which is L, right? So you form the next one. So that process is very similar to the rock, paper, scissors example we did before. So if you keep doing this one, and then you throw this kind of architecture into neural networks and form the layers to handle this one, and that's how you can predict the next word. Okay, so fundamentally, they are all classification problems. Okay, but this one, the every layer or hidden layer in the neural networks, they're trying to store this kind of sequential information based on the previous one and the next one. Okay, where the CNN they just does all the filters, try to figure out the shapes and edges and lines. So as you can see, they use slightly different techniques. That's why this kind of algorithms they're being applied for different purposes. Like the RNN, one good use case would be to handle the time. Okay, a lot of the time we like rock papers. That's the best example because you got to look at the history and then try to predict the future. Like a stock stuff, a lot of those stock simulation or machine learning that also use some time-based kind of models. Okay, yeah, so this one kind of shows the differences. The CNN look at the spatial, all the feature stuff, and form the model, or on the RN, they just handle the previous and next, that they don't have this kind of a spatial kind of feature. All right. So lastly, I did put this example here that if you look at the language model, this was what we did last time, right? So we got all the sentences, the last word to predict, and then we did the vectorizer, And then we use the SVM to train to run this model, right? So if we run this again, all right, so that's what we did. Predict the next word is jump, and we bring some kind of randomness. And then if you use deep learning model, the rest all remain the same thing. Okay, these are all the same. I'm not going to show this one. Also, they use a vectorizer, but the difference is that right here, okay, we are building a sequential model, a neural networks. We added 2 layers, okay, and then the rest remain the same. Okay, so if you run this one, the results are kind of similar. Okay, so they're still trying to do the same thing. Gave that first part of sentence, we output the next word, but this one takes a little bit longer. Okay, the Poly Pomona, the next word is a major. Okay, and this one is one I just did before the class using the RNN. As you can see, the difference is that they use slightly different kind of model. This is the RNN model, so they bring some embedding, they bring some LSTM. I think it's I forgot the term, but that's how you do the RNN model. Okay, so the difference is the model is different, and for the deep learning model, the layers are different, the parameters are different. Okay, so for different kind of problem you're trying to solve, you got to figure out the most optimized configuration for the layers. That's what the deep learning model, what do you need to do for those? You don't have to write those algorithms. The libraries are there, but knowing what layer to use, the parameter to use, that's the specialty. Okay, so that part you just got to see enough examples, experiences. For different type of problem, you should know which one was better. Okay, that's why CNN better for spatial 2D arrays, and RN special good at handle the sequential stuff. All right, but anyway, this is just a really super quick overview. Okay, the deep learning, there are a lot of courses online you can dive into, and they tell you different algorithms, configurations. They probably explain why you choose this one instead of the other one. But for this course, we just want you to know that that is the foundation for the large model. Okay, because when you train those, obviously we need more complicated things like this. That's also you can see why this one takes longer, and that's why they need more computational resources, the GPUs. All right, so yeah, that's where I want to stop here, just to give you kind of quick overview. Okay, so next time I'll look at more examples. We can maybe take a look at how we apply this one to more example in large in language model, and potentially look at how we dealing with the concept of transformers, attention, those kind of things. Okay, so after this week, I think we're pretty much wrap up with all the introduction to machine learning. Okay, so we're gonna move on to more like practical aspects. All right. Yeah, let me just stop here.